So everything seems to have volume. This is up, there's power here. Okay, so new section, section 7.4. Keep in mind that we're almost done. We've got these two sections in Chapter 7. We have Chapter 8, which is applications. We have to do one section in Chapter 9 to do L'Hopital's rule. And then that's it, and we can review. So we will be done well before spring break so that we can review. Yeah, like we will have covered all the material that's on the exam. There will be review work to do every day that if you don't do, I won't be happy. And then after the AP exam, we'll do differential equations, but that just has homework problems. There's no more tests. So there will be grades, as in you have to do things, and if we run out of differential equations things, we'll do something else, but I don't usually run out. All right. So section 7.4 starts with something that actually we talked about a little bit the other day, which are separable differential equations. And basically it means that if I can write the function as f of y times g of x, then it's separable. Okay, so can you think of counterexamples? Does everybody understand what a counterexample means? Somebody tell us what a counterexample means. So, right, it's an example of when it doesn't work. So give me some examples of things that are not separable functions. These are separable. I want examples of functions that are non-separable. Nope, because it would be y equals x squared, and I'd have all my y's on one side and all my x's on the other. Not cosine x, because that would be separable. Or plus y. No, anything where I can't separate them out. Yeah, because like an example of this, like if I had x cubed y squared, that's separable. If I had cosine y times the square root of x squared plus x, that's separable because I have a function that's only of x and a function that's only of y, and I multiply them by each other. Yeah, no, not the square root of x times y, because I could write that as the square root of x times the square root of y. Sure. That's not separable. Anything where I might take the natural log. Okay. So these are just examples. Okay. And so separable differential equations are a whole category of problems. And so it's really easy to solve them because I just say that dy dx is equal to f of y times g of x, or whatever. And I put all my y's on one side and all my x's on the other, including the differentials. And then I can just integrate. And that's really what this is all about. Now, an application of this is exponential change, growth or decay, depending on what k is. X. Spell that right. No, I'm not. Yeah. Exponential? Is that right? That's the word I want. Exponential change. Exponential. Is that the word? I think that's, yeah, okay. Do you ever have one of those things where all of a sudden the word, just no matter how you write it, it looks wrong? All right. So there is a law. I'm not going to risk writing it again. A law of exponential change, which basically says that if dy dt is equal to some constant times y, and y equals some initial value y0 when t is equal to 0, then the solution to my differential equation up here is y is equal to y0 e to the kt. No. It's okay, we're having trouble with that word today, apparently. All right, and really you can prove this quite simply because I can take this and turn it into dy is ky dt, divide both sides by y, and get dy is equal to k dt, and then integrate, right? And what's the integral of dy over y going to be? What? No. It's natural log of y. And what am I going to get on the other side? Nope. K and t are, k is a constant. K is not a variable. So what do I get for the integral of dt? I just get kt plus c. Okay. But I don't like to have, I like to have my y. I like to be able to say y equals. So what do I have to do to both sides here to make that happen? E to the power. E and natural log do what to each other, Zoe? What do? They cancel. They're inverse operators. So what am I going to get? Y. And then this really gives me e to the kt times e to the c, right? Because if I add my exponents, that means that I'm really multiplying the base to each of those powers. Okay, got to remember that trick. No. That's what I just said. It's okay. So what I'm going to do, and this is one of those, I'm just going to keep wrapping up my constants, is I'm going to call this A. Right? E to the c is just a constant. It's 2.7 yada, yada, yada to whatever c is going to be, and it's just going to be another number. Okay, it's just like when I do all those integrals when I'm doing integration by parts and I just make it plus c at the end. No matter how many steps I have to do, I'm just going to do my plus c at the end. Okay. But remember that I have an initial condition, right? When t is equal to 0, what's y equal to? Y0 or y not. And that's what helps me figure out what that constant is. Yes? So if I substitute in here, that tells me y0 is equal to a times e to the 0. What's e to the 0? 1. So that tells me that a is equal to y0 Or my formula is really y0 e to the kt, which is what the law of exponential change says. Okay. All right, we got it? Okay. All right, so we can make this be exponential growth if we let k be greater than 0. We can let it be exponential decay if we let k be less than 0. It just kind of depends on what the problem is. Okay. It is. Are you really cold, Priya? Okay. All right, so I'd like to do at least one of the journal problems here. I'd like to do number 23, which is on maybe page 361. All right, if somebody would read it for us, please. Cholera? It's a hard word. If you don't know what it is, it's a weird word. Cholera. Okay. So, we are told that the number of bacteria doubles or increases by a factor of 2 increases by a factor of 2 every half hour. So part of what this problem is trying to tell you or show us is that we don't always have to use E as our base. That sometimes it makes a lot more sense to use something else as a base. So an alternate formula here is y equals y0, which is the number of bacteria we started with at the beginning, some other base raised to the ht. And the choice for B, or the base, has to do with what happens to your colony, whatever it is, your sample, after every time interval. Because that's really what this is about. Okay, is what happens if I go through, in this case, half an hour. If I started off with 1 bacteria, how many bacteria am I going to have after half an hour? And after another half an hour? And after another half an hour? Okay, so that was 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So whatever my factor of increase is, however my bacteria, by whatever factor my bacteria grows every time interval, that's what I want B to be. So I'm going to let B be equal to what in this problem? 2. Okay. Y0 is the number of bacteria we start with, which is how many? 1. That's what the problem tells us. And then the only tricky thing that's left is H. And you have to remember that H is the reciprocal, or 1 over the amount of time for the sample, just so that it's a little more general. Hang on. For the sample to change by whatever that factor B is. We'll get to T, we can talk about T in a minute for you. Okay. B is how the sample or the colony changes every time interval, right? Okay, so in our case it doubles, that's a factor of 2. But H is 1 over the time it takes the sample to increase by 2. So how long does it take the sample to increase by 2? Half hour. Well, T's are variable. T is time. And so if I want to know how many there are after 100 hours, then I let T be equal to 100. So what we're doing right now with B, Y0, and H is setting up an equation that I can use to figure out what's going to happen in any situation like this. It matters in that H and T have the same time unit. In general, it doesn't really matter what that is. But that's a very good question. Okay, so what's H really going to be equal to here? Bless you. 2. Okay, so my equation becomes Y is equal to Y0, which is 1, B, which is 2, raised to the 2t. Okay, we just took this equation up here and filled in the stuff that we know. And then for part A, we're supposed to find Y of what time? 24 hours. Okay, so that's going to give us 2 to the 2 times 24, or 2 to the 48. And what are we going to get? Yep. So that's like, I can't even say. I think we're talking almost a million billion. The trillion would be 12, so it would be 280 trillion, because a billion is 9. So that's a lot. Okay. I don't know. But how does it answer B? Yeah. So it doesn't matter that even though your body swings, your immune system swings into action and says, I'm going to kill these things because they don't belong here, your immune system kicks in, it's still making so many that it overwhelms your body. Okay. Cholera is particularly virulent. Really? Was there a cholera epidemic here? There probably was. I believe it's like a gastrointestinal thing, as I recall. So it's, again, spread with the non-washing of hands. have a friend who's a medical librarian, and she works with a medical historian who believes that the greatest invention of modern medicine is getting people to wash their hands before they eat. That has made the biggest impact on people's lives, is getting people to wash their hands with soap before they sit down and put stuff in their mouth, which is kind of simple and amazing. But okay, so what? Yeah, but if you wash your hands in your shoes. Okay, so I'm going to stop here because we don't really have time to do Newton's law of cooling. Please make sure that you read for Wednesday. Enjoy your lovely 5-day weekend.